Our first true computer was the abacus, but not only the physical object, but also the whole tools for representing abstract quantities. Okay, it starts like this. You start counting things with finger, okay? And then you have one representation for a finger, like one stick. It starts like one stick represents one thing, one sheep, one sack, one grain. Then you understand that 6 sticks will represent a small little horde, your family, the quantity of flowers you have in your garden. And then that's the easy part, because it gets more complicated as you invent another symbol that represents the first 10 units of the first symbol. And then you have yet another symbol that stands for 10 of the previous symbols. And it goes on with bigger and bigger symbols representing quantities of the previous symbols. And anyway, it gave us the abacus, and the abacus is a truly wonderful little machine. First, it's highly portable and doesn't need battery. And then, because just as you finish typing the numbers, it gives you the result, it has a zero computation time, which means it is still the fastest computer we have ever built. Also, the abacus can count up to the million digits, and some up to the trillion. That's way above the kind of quantities an average user at that time was going to deal with. So, if the abacus is so great, why didn't we stick to it? What's its problem? What's its limitation? The abacus has a really serious limitation, and it has nothing to do with buying and selling cattle. It has to do with the concept of infinity. Imagine this riddle. You are a horse rider and you want to get to a distant city. But there's a point in your travel that you reach the middle of the distance. Let's suppose that there's something out there. And when you reach there, you see that you still have something to cover. You have still some distance left to go. But before you actually cover this whole distance you have left, you have still to cover half of this distance left. And when you do cover this half distance, you have another half, and yet another half, and yet another half, which means that because you take some small time going to point, you never, and because you have endless fractions of points to go, you never reach anywhere. This riddle was proposed in the 4th century before Christ by a Greek named Zeno, and it was interesting not because the Greeks really thought that they couldn't move, but because although they could intuitively know that there was something wrong, they didn't have a vocabulary to pinpoint where exactly was the error on it. So let's try to understand this with the tools they had at the time. Those are Egyptian numerals, although they used Greek one. Okay, you have a distance between you and a city, and this distance is represented by a symbol. And when this distance gets smaller, you have to change the symbol for another one, representing a totally different new quantity. And when it gets smaller and smaller, you keep on changing symbols for complete different icons, meaning other things. And then you reach a point where you don't have any more symbols, and you start representing a fraction of distance because it's less than 1. And you represent fraction in the same way. You have a symbol for a fraction, meaning 1 divided by, and then you have a lot of other symbols. So you have a symbol meaning 1/100th, you have a symbol meaning something really small, and then you will reach sometime or other the end of your vocabulary, the last icon, one icon which means a number really small, or something so small that you can't count on it, and that limit was about the million, or 1 divided by 1 million. You see, that's the problem. Each icon has a different story, and if those stories made up a comic strip, you couldn't tell where was the end of it. You couldn't really tell where the story was leading to. And because of this limit, it's really hard to really grasp the idea of infinity, because you don't have the vocabulary for it. Then came the zero, a symbol that represents nothing, but allows us to understand any quantity with just 10 icons. And because of that, answering our silly riddle became a child's game, because making one number becoming smaller and smaller and smaller and smaller, you just have to add another zero after the dot. And then it's clear that looking at this, at some point the number will become zero, and when the number becomes zero, you have reached your destination. What's the point in this? What happens when you simplify the use of a certain technology?